Hello everyone. Today I want to talk about a project that I have done actually many years ago, I think 10 years ago, and it's about making elemental sodium by electrolysis. This project was pretty cool, but also pretty dangerous, and I invested really a lot of time into this project to make it working. So I want to share all the research results with you. And after watching this video, I hope that I give you enough information in order to make your own Castner cell. So what you can expect is to be able to create your own Castner cell with a output of about 100 to 150 grams of sodium per day. So first of all, I want to show you some images how the Castner cell looked like. Apparently, because this is a very old project, the Castner cell doesn't exist anymore because all the parts I have used for some other projects. And anyhow, in the old days I couldn't buy sodium, but nowadays I can buy sodium, so I don't mess around anymore with distilling it. But I know that there are many places in the world where sodium is not um, easily available. So in this case, building your own Castner cell is still a good choice in order to make your own sodium. So this is how it looked like. Basically, you see the cell in here. Um, Basically, this pot was just an insulator. It was filled with sand. And in this part, you see the temperature regulation, and this is the thermocouple here, goes up there. The temperature regulation I will discuss in detail because actually the temperature of the whole cell is a crucial thing in order to make everything work. So I spent, I don't know how many hours, at least hundreds of hours in trying to find out, trying to fine tune everything, and this was really a mess. But in the end, I got it working. So here I'm getting all the temperature values from the microcontroller, and I'm programming that stuff. This is another look on the Castner cell. So basically here I was scooping out the sodium. And this is a close view of the Castner cell. You see here, this is the anode, and the cathode you can't see from this view, and here is the thermocouple to get the temperature of the melt. And this is the outer heating element, and this is the sand insulator here. So now we are coming to the key rules for construction. So you really should use a thermocouple to measure the temperature, because I told already that measuring the temperature and regulating the temperature is a key criteria to make the whole project work. Because the problem here is that the operation temperature should be between 320 and 330 degrees Celsius. So you see there is just a very narrow range of 10 degrees to make everything work. If the temperature is too low, it will not work because the sodium hydroxide will solidify. If the temperature shoots over 330, the sodium will melt into the sodium hydroxide, and it's equally a mess, and you will not be happy at the end of the day. So temperature regulation is very critical in that project. The initial voltage after the melt should be 3.3 volt. This is to get rid of the water. Actually, at the first melt, when you melt all the sodium hydroxide, don't set the voltage to the 4.5 volt where it produces sodium, set the voltage to 3.3 volt till you realize a significant drop in the current that is drawing the system. Why? Because sodium hydroxide will draw some water from the air and there will be some water in the cell. And in order to get rid of the water, we should start with a lower voltage, because with that voltage only the water is getting electrolyzed, so split up to hydrogen and oxygen. When you realize, or when um, when the current drops down significantly, then it's done, and then you can increase the voltage to 4.5 volt to produce the sodium. If you're not doing that, then you can have some explosions, bigger explosions, smaller explosions, and um, especially when you have a small cell, you really don't want to have explosions because the cell can eject the molten sodium hydroxide, which is really, really a mess and really shitty and really dangerous. You don't want to have that. So take this safety step and do um, the 3.3 volt to get rid of the water. Otherwise, you're going to have problems. And the anode should be nickel. Actually, I didn't have nickel. I used stainless steel and I made a nickel plating on the stainless steel, which worked equally fine. The cathode can be stainless steel or copper. I have used stainless steel, but apparently copper is also good. The cathode should come from the bottom. I will explain this in more detail shortly, but this is very important. And I think that if I would build the cell again, I would definitely not build it as small as I have built it, because the bigger the cell is, the less risk of explosions you're having. Because the explosions actually they will still happen, but because everything is bigger, the chance is less that some molten sodium hydroxide will get ejected while the explosion. So simply build it as big as possible. Probably if I would build it again, I would build it 15-20 liters, something like that. My design here just had about 3 or 4 liters, I think. So something about safety. Messing around with molten sodium hydroxide is really dangerous. And explosions do occur, so they happen. And if you're standing close to the cell and you have an explosion, it's very likely that some molten sodium hydroxide is getting on you, and that's something that you don't want to have. In this kind of sense, eye protection is an absolute must. And I realized that you should also wear a respirator, because the cell will create some sort of spray. So there are tiny particles of sodium hydroxide in the room. They are airborne, and when you breathe them in, they're burning and it's really nasty. So a respirator is a good idea to have. And actually, you really should have a thick full body protection when you're close to the cell, because it's really so dangerous. And if you have molten sodium hydroxide on your skin, it eats away the flesh like nothing. So if you're going to build a thing like that, invest first and foremost in safety. So before I continue to show you some more pictures, I want to explain the basic functionality of the Castner cell. So what you see here, this red stuff, that's basically the anode. What you see here, this blue thing here, that's basically the cathode. And the gray stuff, it's just normal stainless steel, and it's not connected to the anode and not connected to the cathode. And Here, what you can see here, that should depict the molten sodium hydroxide, and this stuff that should depict the liquid sodium metal that formed. So how does it work? The electrolysis is happening between the anode and the cathode, and on the cathode the sodium metal will form. So there are tiny little droplets of sodium that form, that combine, and because sodium metal is lighter than sodium hydroxide, these tiny bubbles of sodium will go to the surface, and at the surface they will combine, and then you can scoop them out with a special spoon or with whatever kind of device that you have made. When designing a bottom-up electrode, there is always the big question how to insulate this electrode. And Castner came up with a very smart solution. He just used a somewhat long tube in order to contain the cathode. So this tube doesn't touch the cathode, and when the sodium hydroxide starts to melt, it will flow inside this tube. But because you're having a temperature gradient, meaning at the top here it will be hot, but 10 centimeters lower it will be already significant cooler, so the sodium hydroxide will solidify here, and you're having a perfect insulator, and you don't need to take care about the sodium hydroxide eating away your insulator. So this is a very cool thing and a very good idea that Castner had here, and it works really fine. Yeah. So coming to the chemical reactions on the cathode. So the main reaction that we want is that the sodium ions are getting reduced to metallic sodium. But apparently we are also having some other side reaction that we do not particularly want, but they are actually happening. If there is some water in the cell, the water will be also electrolyzed and hydrogen will be generated at the cathode. The hydrogen will bubble up, and water can also react with sodium to form sodium hydroxide, which will also generate some hydrogen. And sodium can also react with sodium hydroxide to sodium oxide, which will again produce hydrogen. So we see that basically we are having two things that are generated at the cathode. It's first of all the sodium that we want, and then we have hydrogen being generated there. The hydrogen is actually kind of useful too, because it will prevent the sodium from being oxidized from air coming in. However, the hydrogen is also pretty dangerous, because I had one really big explosion when I tried to contain the hydrogen in order to protect the sodium layer a little bit better. So I put a lid on it, and so the hydrogen couldn't escape, and at some point, it just ignited and it was a huge explosion, and material got ejected from the cell, and it was a total mess and very dangerous. So this means that I didn't have all bugs out of the system, but still it was working. Now we're coming to the other side, to the anode side. If there is some water present, like in the beginning, some oxygen is generated, the nickel will react very slowly. So nickel is very good because it's actually one of the best materials for the anode, but eventually it will also react to nickel hydroxide. If there is some sodium flowing around, the sodium will react with oxygen to forming sodium oxide. And if there is some water present, sodium oxide will form sodium hydroxide. So now we are going to discuss the heating of the cell, it's actually apparent that we are having two heat sources. First of all, the external heating, and then the heating caused by the electrolysis. And in order to master the process, it's very important to understand and to take both um, into consideration and to control both of these heatings um, to make everything work smoothly. So here you can see the external heating of the cell. It's just some nickel chrome wire that is wrapped around the cell with fiberglass as an insulator. If you choose the same design, then it's just important to don't overshoot something like 800 degrees, because the wire will otherwise melt the fiberglass and then the wire will short out with the cell wall, which is not good. So just make sure you stay under 700 degrees, then everything is fine. To the external heating. If you start the whole system, then you're in the initial heating phase, meaning the temperature will slowly rise up from room temperature till the point where all the sodium hydroxide is molten. That could be possibly at, I don't know, maybe 350, 360 degrees, whatever, to make sure that all that stuff is really molten. When you reach that point where everything is molten, you can deactivate the external heating. And at the same time, you start electrolyzing with 3.3 volts. If you remember, the 3.3, that's the voltage where we get rid of the water that's inside. It will not produce any sodium yet, but it will produce oxygen and it will produce hydrogen from the water in the cell. So at that point, the temperature will start to drop because the current will not be that big, and you will realize that the current will get less and less and more little and more little, because all the water is getting out of the system, and at some point the water is out. Yeah, but just to explain the heating regulation of the external heating, when the temperature should drop beyond 315 degrees, because there is a chance that it solidifies again, you have to start heating. And you have to stop heating again at 320 degrees. So the actual electrolysis should happen between 320 degrees and 330 degrees. So you're having just 10 degrees for the electrolysis. And usually the electrolysis is generating also heat. So normally when the system is operating well, theoretically you just need the initial heating to get everything into a melt. And then if everything works well, only the electrolysis heating should work, because the electrolysis heating should put enough energy, enough heat into the system to keep everything molten. If that's not the case, then it's still good to have this other temperature regulation here. So if the temperature should drop beyond 315, it should start to heat it up again to 320. Okay, now we're coming to the electrolysis heating. So you see that we are just having a very narrow gap of 10 degrees. This is really not much. And when we start the electrolysis, the temperature will rise, and at some point it will overshoot to 330. depending on your power supply. You know, maybe you're having a weaker power supply and it won't overshoot, or it will, I don't know, do whatever it does. However, we should end the electrolysis when it overshoots 330. And then we are not doing anything, the machine is not electrolyzing till we hit again the 320 degrees. At 320 degrees we are activating the electrolysis, producing sodium, deactivating. Here we have deactivated it, temperature is falling, and we are again activating it. So we are not producing sodium all the time, we are just producing sodium in time intervals. So in terms of heating, I had my control unit here. This Arduino microcontroller was reading the temperature from a thermocouple. It was here. And yeah, basically simply processing that values and controlling the power to the external heating and to the electrolysis. So you see that I have here a relay and here I have a relay. So two relays. One relay is for controlling the external heating and the other relay is for controlling the electrolysis. So you need to have at least these two channels to control the power. And actually, you know, if I would redesign the system, if I would build it again, I would not only have one thermocouple, I would have more thermocouples, at least one in the anode chamber and one in the cathode chamber. The electrolysis was actually drawing about 40 to 50 amps, so make sure all the cables and the connections are dimensioned accordingly. Otherwise, yeah, some cables might melt or do whatever. So what you can see here is part of the anode. So the anode is this upper part here, these connectors down here, and this tube or pipe here. And this lower part, it's very important to be nickel or nickel plated. Stainless steel is also okay, but stainless steel will dissolve rather fast. But as long as it's replaceable, it's also not a big deal. That's the bottom view of the thing, and basically you see that the anode here is not connected with this steel plate. You know, this steel plate will be put on the chamber, so it's insulated with some insulators and not having a connection. That's also very important, otherwise the entire cell will start to act as an anode, and we don't want that. That's the top view. Again, you know, this upper part, the upper disk, is the anode. This disk here, it's just neutral. It's not connected to the anode. It's not connected to the cathode. The same as this main pipe here. This is where the sodium will collect at some point. And again, the lower part is the anode, where the magic is happening. So what you can see here is the bottom immersed cathode and the entire chamber. I have actually plated the entire chamber with some nickel plating in order to protect it. Here you see the cell when it's getting filled with sodium hydroxide. So I have some sodium hydroxide flakes, and yeah, I was melting that stuff. It took about 1 hour or something like that to melt everything, and then After it was molten the first time, the anode got inserted. This is a nice image because what we see here is the cathode tube, and actually with the colors here you can really nicely see the temperature gradient. So at the top part here it's still hot, you know, the sodium hydroxide is possibly still molten here, and when we go down here it gets cooler and cooler and cooler, and at the bottom side it's possible to touch the thing. It's not hot anymore and everything is perfectly insulated. So it's really a cool idea from Castner that he had there by designing the cell in this way. So what you can see here, this is the power supply that I have built for the electrolysis, and it's not a high-tech thing. It looks pretty fancy, but it's pretty it's a pretty low-tech thing. Um, you really can't see it very well, but what you see here is a microwave oven transformer, and I simply took out the secondary, so where you have the high voltage. I took out completely and I made a couple of windings with very thick wire. I don't know what it is, maybe um, 25 square or whatever kind of stuff, you know, 5, 6 windings, and that was basically the transformer for the AC, for the low voltage AC. And what you can see up here, you know, these 4 coolers. On each cooler you have 3 diodes, so it looks pretty fancy, but it's a very straightforward full bridge rectifier. So you can use a microwave oven transformer, kill the secondary, um, make a couple of windings, and just do a full bridge rectifier, and it will work really fine. So generating between 30 and 50 amps with this device was not a problem, so it was perfect for the electrolysis. So this is one of the few pictures from the cell being in operation. When we zoom in here, we can clearly see the bubbles which are caused by the hydrogen coming up here. And if we have a closer look, then we also see some small sodium globes. So here, for example, and here. But there are actually much more sodium globes. They are just hiding behind the bubbles, the hydrogen bubbles. So if you scoop in, if you wait a little bit, scoop in, get that stuff out, then you're having some sodium for sure. Actually, these small tiny bubbles are also causing the problem with the sodium hydroxide spray in the air, because each bubble bursting will create some spray. So some tiny chunks of sodium hydroxide will be airborne and being carried out by the hydrogen, and when you breathe that stuff, it's really not good to breathe it, so wear a respirator. So in the end of the video I want to talk a little bit about the bugs and drawbacks and possible improvements that are possible to make. The first drawback is that the cathode chamber is actually open, and the sodium metal can be easily oxidized by the air circulation within the chamber. I initially said that the hydrogen that is generated here in this chamber has some protective properties for the sodium. Indeed, it does. It does protect to some degree, but because the hydrogen is moving up constantly, we are having a kind of circulation in this tube. So that means hydrogen goes up, air comes in. And when the sodium, which is very hot, uh, touches or gets in contact with air, it's oxidized very, very, very fast. So you can see the sodium globes appearing but also disappearing again because they are simply oxidized very, very fast. So in order to keep the sodium from being oxidized from the air circulation, once I had the idea to just put the lid on the tube in order to contain the hydrogen a little bit better to protect the sodium. Apparently, it did work to some degree, but at one point I had a major explosion because here in this tube there was accumulating a lot of hydrogen, which I wanted, but in general, hydrogen and oxygen and high heat and sodium metal, it's not a good combination. And at one point, simply the hydrogen ignited and I had a big explosion, which due to the shock wave that was generated here, it pushed down the molten sodium hydroxide, and some of the sodium hydroxide was ejected by the cell. Luckily, at that point, I was not in the room, but it was a big mess in my workshop. So in order to solve this issue, if I would build the cell again, then I would probably come up with a solution like that. So I would just here um, somehow put a vessel filled with paraffin oil or some other mineral oil. Then, first of all, have a closed cathode chamber, and then it would be good to have an exit from the cathode chamber going into the chamber with the paraffin oil. So basically something where the sodium can go here. This here is the level of the paraffin. So when the sodium hydroxide is getting electrolyzed, sodium is generated, the sodium floats up, and when the sodium is above a certain point, the sodium will start to float into the chamber filled with paraffin oil. I have never tested this. I don't know if it's a good idea or not, but I know that the open cathode chamber has some drawbacks. And another change that I would do if I would design the system new from the scratch is to add more than one thermocouple, because I had um, the thermocouple in the anode chamber somewhere here, but that means I was totally blind about what temperature there is in the cathode chamber. So I would at least have two thermocouples in a new project. Another change that I would do is to build everything a little bit bigger, because um, a small cell is always a little bit dangerous in terms of explosion. If you're having explosions, then a small cell is more likely to eject some sodium hydroxide somewhere. A bigger cell may contain the explosions a little bit better than a small cell. Additionally, a small cell, you're messing around for where I should put the thermocouple, where I should do that, how I should do that. And with a bigger cell, you simply have more space, also more space for adaptations. And yeah, in general, uh, building stuff bigger is always a good idea to make it work. Just some final words about safety in the end. Um, it's very likely that at some point no matter how well it is designed and how good the concept and everything is, there will be some explosions and some accidents. So it's a very good idea actually to invest in safety equipment. I mean, really good safety equipment, not only safety goggles, but really a full body protection when you're going to play around with that stuff, because it's just inherently dangerous to be close to it. And so good luck and goodbye.